Hi, everybody. I am Ted McKlveen, the co-founder and CEO of Verne, and I'm excited to talk today to you about our high-density hydrogen storage solution for heavy-duty transportation. What really has motivated Verne and got us in this business in the first place is addressing climate change and the significant amount of emissions contributed to our global warming by heavy-duty transport, with over 10% of all global greenhouse gases coming from trucking, shipping, and aviation. What makes this even more challenging is that these sectors are particularly difficult to address. These emissions are hard to address with currently available battery electric technology. What gives us a lot of hope and promise, though, is all the momentum we're seeing building within hydrogen and across these sectors, but specifically within heavy-duty trucking. So you'll notice a handful of the articles on the right there, just some of the recent public announcements within hydrogen for heavy-duty trucking. On the top, we have Hyundai and Hyzon with commercial sales on the road today, as well as really the big OEMs and tier ones all launching hydrogen truck pilots. But while these pilots have proven the feasibility of hydrogen, and while some commercial operations have shown that hydrogen can work on the roads, there are numerous challenges today with the current hydrogen technology that's limiting their broader applicability and the real ability of hydrogen to address this important climate crisis. So based on the way that hydrogen is stored on board today, which is as a compressed gas, three problems emerge. First, there's low range. Current hydrogen trucks can only travel close to 400 miles, which is well short of their diesel equivalents, which can travel 1,000 miles per fill. Second, the payload is reduced. These hydrogen tanks, because they're heavy pressure vessels, cut into the amount of payload that the truck can carry. And finally, the tank systems themselves are expensive, well above where the Department of Energy thinks tanks need to cost for hydrogen to be economic today. Due to all these challenges, a lot of the leading truck OEMs are investigating new ways to store hydrogen on board at a higher density. So you notice just a handful of the logos on the right, really representing some of the leaders in this space, all expressing some interest in higher density technology. And where this leads most of these manufacturers is to liquid hydrogen. Liquid is the obvious next step, as liquid hydrogen provides higher volumetric and gravimetric density and a lower hydrogen tank cost, seemingly addressing the problems with onboard storage today. But liquid introduces some challenges that were not encountered with compressed gas. With liquid, there's operational flexibility hits, as you have to consider how your liquid will boil off or evaporate over time. The hydrogen itself can be more expensive due to the high cost of liquefaction. And most importantly, there's very little liquid hydrogen available globally today. To go a bit more into that last point, taking a look at the map here of the current liquid hydrogen supply, there's only enough liquid hydrogen supply globally today to serve 7,000 trucks, well less than 1% of the global truck fleet. And while some may advocate for building out liquefaction supply, and while some of that's important to do, building out supply is incredibly expensive and will take a while. The latest and greatest liquefaction plant built by Air Liquide this year in Las Vegas cost $200 million and will only have the capacity to serve 600 more trucks. All this to say, what the fuel cell truck industry really needs is high density hydrogen, but easily accessible access to high density hydrogen. So this is where Verne comes in. What we're building at Verne is called cryo-compression. It's high density, but without the liquid hydrogen limitations. This chart here has a lot going on, but to walk into a bit here, on the x-axis, you see temperature, and on the y-axis, density. On the far right of the graph, you see where compressed gas hydrogen is at 285 and 285 approximately room temperature. You see even the 350 all the way up to 700 bar really has limited density, limiting the amount of hydrogen you can carry on board and leading to all problems I've talked about earlier. On the far left-hand side of the graph, you see liquid hydrogen. Liquid hydrogen is at that much lower temperature at 20 Kelvin and is permitting a higher density, close to 70 grams per liter. Just above where liquid hydrogen is in terms of density is cryo-compression, where Verne's operating. We're able to achieve even higher densities than liquid hydrogen while at more moderate temperatures and at a slightly elevated pressure. So I'll talk more about this cryo-compression system, but what Verne is providing really is two elements here. First, the onboard hydrogen storage system, which you can see on the left, storing hydrogen in this cryo-compressed state. You can see an example tank set up there with multiple tanks that store the hydrogen at that compressed and cold state, maximizing the onboard storage density, as well as the required equipment to refuel the hydrogen in this manner. So whether that's a liquid supply of hydrogen using commercially available technology or a gaseous supply of hydrogen using Verne's cryo-compressor, enabling somebody with a cryo-compression tank to refuel at any station. So to dive into the first part here, the onboard tank. In order to store hydrogen as a compressed gas that's also cold, we need to have both a pressure compatible element as well as insulation. And to have all the materials on board be compatible with both high pressure and low temperature. Here you see an example of our tank where you have that inner compression vessel surrounded by highly technical insulation and the cryogenic compatible valves. What this means for a truck operator, we can see from looking at a current truck on the road today, the Hyundai Accent truck, which is carrying approximately 35 kilograms of hydrogen, and it's doing so across 7 compressed gas hydrogen storage tanks. If we were to substitute those with Verne storage tanks, we could store 10% more hydrogen in only 3 tanks. So because we're decreasing the number of tanks so substantially, this would cost 40% less, would eat into the payload 50% less, and would take up 60% less volume. Additionally, these tanks have inherent safety advantages over compression systems. Alternatively, a truck operator could opt to store more tanks and double their range. So this higher density, really double the density of compression, offering numerous benefits to a truck operator. Looking now at the supply side, we know that there's 5 ways that hydrogen can arrive at a hydrogen refueling station. It can arrive as a liquid, a compressed gas, or be delivered as a compressed gas in a pipeline, or be produced on site with electrolysis or another method such as steam methane reforming. Now, if you're going to store hydrogen on board a vehicle as a liquid, you must have that delivered to your station as liquid, since we don't have small-scale distributed liquid hydrogen. So the only suitable delivery method for hydrogen to a station with liquid onboard storage is liquid delivery. If we switch over to cryo-compression is compatible with any way that hydrogen could arrive at the fuel station, really opening up the potential footprint for hydrogen and hydrogen-based trucks to operate. The way that these trucks would be refueled at a station that doesn't have liquid supply would be with Verne's cryo-compressor. This takes hydrogen that is at your station, whether that's delivered via pipeline or produced on site, cools and compresses that hydrogen, and then reaches that high density state, which is used to fill our tanks. So to summarize here, we have ways to fill our tanks, whether there's gaseous supply of hydrogen using Verne's cryo-compressor, or a liquid source of hydrogen using a commercially available cryo pump. Speaking now a bit about Verne's business model, there's really these 2 core pieces of equipment which we sell. And so we sell the hydrogen tanks to truck fleets, and we sell the station equipment, the cryo-compressor to stations, whether that's privately owned or public station. Because we have this touch point at both the supply and the demand side, we're in a unique position to really service some of the connectivity between these 2, helping the stations increase utilization and helping fleets have assurance of their hydrogen supply and enable them to broaden their operation profile. So with these 2 connectivity points, we're offering the fleet card, connecting the fleets to stations and forming the Verne fuel network. Looking across these 3 different product offerings, the onboard tanks, fleet card, and station equipment, Verne can access a $28 billion per year total addressable market within Class 8 trucks alone. When we think about other nearly adjacent markets, such as Class 4 to 7, mining haulage trucks, and even going into maritime and aviation, the market substantially grows as does the climate impact. So far, we were founded in 2020, and over the course of that year, we raised funds and recruited really a team of the global experts in cryo-compression technology, and have grown our team to 6 team members so far, and got early funding from the National Science Foundation in Stanford. Over the course of the last year, 2021, we continued to raise funds for the team, as well as build our first full-scale prototype, which we'll be testing later this month. And we're thankful to just be able to announce funding from the Breakthrough Energy Fellows. In 2022, we will be piloting our technology on board with different vehicle OEMs, and from there continue pilots and tests as we work to scale up our manufacturing and achieve certification. To speak briefly about our team, as we wrap things up, I got a chemistry degree at Harvard and went on to work at an energy storage startup here in San Francisco before doing my MBA at Stanford. I'm joined by co-founder David Jaramillo, who got his PhD in hydrogen storage from UC Berkeley, as well as COO Bav, who is a renewable energy engineer and also got his MBA from Stanford. Our technical team really brings a lot of decades of hydrogen storage experience at Lawrence Livermore National Lab, Worthington Industries, as well as vehicle experience from Stellantis, Jeep and Ram, as well as McLaren, and a great suite of advisors. I would really welcome the opportunity to speak with any of you at the event, or for you to reach out and ask any questions. I'm sorry I couldn't be live today. But I wanted to mention the things that I'd be interested in talking about would be any pilot opportunities, demonstration projects, fleet connections to end users, as well as funding opportunities. We're not immediately fundraising now, but we'll be looking to raise funds in the early spring, late winter of 2022. Thank you, and I look forward to speaking with you and meeting you all on the 17th.